Okay, we'll start now. So, we were discussing about this detection. We were discussing about this detection thing, right? So, what we are discussing is about Bayes detection, right? So, it is based on this Bayes cost function, right? So, it is going to be like this, right? So, C bar is a Bayes cost here, right? So, that is given as this prior probability not, right, and you are telling some, I mean, error in it, right, probability, right, when 0 is transmitted but your y lies in the region gamma 1, right, plus we have pi 1, and then it is a gamma naught here. We can have, like, that cost associated with this. Your originally it is 0 and you are declaring that it is 1 here, like this, and here let me write it here again. This is pi 1, and here you are having, originally it is 1, you are declaring that it is 0 in this, right? So it is like this, a cost. Of course, we have C00, C11, that is normally chosen as 1 here, right? So once again, I'll explain you what is this. This is basically what we call it as this Bayes cost associated with the detection, right? You need to do the deduction that minimizes this Bayes cost. What is deduction theory basically, right? We have the random variable x associated with the transmitter section, and you have this receiver section random variable y, right? And the observation set in the receiver section, right? So that means that the outcome of this random variable y, the outcome of this random variable y, right, you are going to do some partition. Let us say that it is the outcome of the receiver, right, the random variable y, if it is spanning that range, right, like minus infinity to plus infinity, right, your goal is to partitioning this observation set into two parts. Say for example minus infinity to some point here, right, say it's like, some sort of thresholding, right, this one we can say that it is gone, and you have here, this is going to be your gamma 1. You are dividing whatever you are observing, that you are dividing into two parts. That is what the thing is, what we call as partitioning this observation set into two parts. One is gamma naught, the another one is gamma 1. How we interpret this gamma 1 and gamma naught? In the receiver section, that value, that outcome, what you observe, if it lies in gamma 1 region, right, whatever instantaneous observation you are having in that receiver region, if it lies in this one, you can actually decide whatever is being transmitted from the transmitter is actually 1, right? So if it lies in this region, we say that whatever is being transmitted from the transmitter is 1. If the observation lies in this region, we say that whatever is being transmitted from the transmitter is 0. So the detection rule, right, the is actually the requirement to find out this set, basically this gamma naught and gamma 1. That set only you are trying to find, means you are trying to find out indirectly this YTH. For this task, finding out this threshold itself is actually helps you to give the two set here, like minus infinity to YTH, right? So this belongs to the set gamma naught, and YTH to infinity, that belongs to this gamma 1. We are actually dividing them into two set here. That's the idea, right? So it is not necessary that you will always end up with what only one threshold to get this, right? This partition. You can have more than one threshold also, but whatever is needed is you have to divide them into gamma naught and gamma 1. That is the thing. The complete observation you have to divide them as gamma naught and gamma 1, right? So some way we need to find out this gamma naught and gamma 1, right? So the methodology what we are going to use to find out this gamma naught and gamma 1 is to choose this Bayes cost. So what is the, we are actually giving a penalty for doing this error by doing wrong, the error in detection. We are giving that penalty for it. Error in detection, we are giving the penalty for that, right? And that penalty, right, we are trying to minimize that, right? This Bayes cost we are trying to minimize. What is there in that Bayes cost? You have here the error involved, this probability of this error involved. What is that error? The error is basically you are transmitting 0. What is that subscript indicate that you are transmitting 0, but whatever that observation in the receiver section, right, it actually falls in the set gamma 1. It falls in the set gamma 1. That is actually error, because if it lies in this gamma 1, then you know the rule that you have to decide whatever is being transmitted in the transmitter is 1 only, right? So but it's not true. The true is you are actually transmitting 0 only, right? So now when you transmit 0, when you are transmitting 0, that is the meaning of it. When you transmit 0, right, it is like a conditional probability, right? When you transmit 0, your random variable y, the outcome of the random variable y, if it lies in the region gamma 1, it will end up with what? Error. This is error. And similarly, here you are actually transmitting 1. You are transmitting 1 here. This is what you are transmitting. And your observation y, right, it lies in the region gamma naught. That's also error, right? So this is also the error here. So this is also the error here. This is actually that error. We give different name for these two errors, right? So in this case, in radar terminology, in the radar, right? So what we say that the target is the absence of target. The target is actually not available, but you are saying that the target is present. The target is not there, is absent, right? Is not available, right? But you are declaring that it is available, right? It is like that, that is a decision. So what does it mean? It is basically that false alarm, right? So you are having this alarm error in that case, right? So in this case, p naught of gamma 1 is basically this probability of false alarm, because the target is not there, but you are saying that it is. Comes to this p1 of gamma naught, right? The target is actually present, but you are saying that the target is not there. This is called this probability of miss, right? You have two different types of errors involved in this, right? So now we have what is called the cost associated with that, C01, C10. depends upon the importance. As you know, in the previous class we discussed that it is very crucial to, right, compared to this false alarm, right? False alarm is okay, fine, comparatively, right? But it's the target case, I should actually assign two different constant here, C10, C01 need not be equal always. But in digital normal telecommunication, if I am transmitting ones and zeros, in that case, if both one as well as zeros are important, equally important, there is nothing like presence and absence in that case. It is not the radar application. In that case, C10 as well as the C01, you can identically make it as 1, right? So in that case, that importance are equal. Otherwise, you have to give something like 0.9, 0.8 or 1.9, like that. You can give it as a value less than 1, but two different values you can assign it for C10, C01, depends upon the application, right? It depends upon this. And not only that, it also depends on the prior probability. This pi naught and pi 1 is not just pi, right? So don't confuse with this 3.145. This is the this is a symbol what I am using here. Naught is the probability of 0 being transmitted. The probability of 0 being transmitted from the here, right? So it is a prior. Pi 1 again, it is a probability of ones, right, being transmitted from the transmitter. It is like that. So this is what we are having, this pi naught and pi 1. Let us assume we are giving equal weightage, right? C10 and C01 both are equal. In that case, you are getting this expression C bar, that is equal to pi naught, the prior probability, P naught of gamma 1, pi 1 into what? P1 of gamma naught. So we have this expression like this, and you wanted the problem now boils down to a very simple statement. You need to get this gamma naught and gamma 1, gamma naught and gamma 1, such that this cost function C bar is getting minimized, and that is what we call it as the Bayes rule, Bayes method for deduction rule, right? This is the thing, right? But remember that it depends on the prior probabilities also. It is very important that you have to see that it also depends on the prior probability, right? So with this context, actually we discussed one example for the discrete memoryless channel, how we can actually do this deduction rule for discrete memoryless channel. We will continue that actually now today also, right? So we'll see the case now. So we'll quickly recall what we discussed in the previous class. This one we already discussed, right? So this one told, right? So now coming to this discrete memoryless channel, for this discrete channel, right? So what is given to you is the channel characteristics, right? You are given a channel characteristics. This is the channel characteristics here. This is about the channel. You have to be careful, right? This is 0 and this is 1 here, and what you see here, this is 0 and this is 1 here, right? So this is the channel characteristics, what is given to you. And you have this observation, right? Y in the receiver section, what is being transmitted is X here, right? And now you have the detector block here. This is that Y is actually given to this detector block for doing this detection, right? Detector for taking this detection, the actual detection we have to do, right? So the possibilities, we have only two choice for this Y, right? Either 0 or 1, that is what is as an input to this detector. So the detector job is to, right, check, right, whether I can treat that 0 as 0 as such, or we have to invert it, right? So that way, so we need to have some rule for this detector, right? Possible rules I can assign, because it is a simple binary, right, data whatever we are having, and it is going to be a discrete memoryless channel. In this particular case, what are the possible rules I can impose for this detector? Right, you have four rules here: rule 1, rule 2, rule 3, and then rule 4. What is that? You know that our rule, I mean the deduction theory says that we need to do that, we have to identify this partition set. Let us say 1 and gamma naught, they are all the partition set here, right? So what are all the possible combinations we can have? So that is what we are discussing. We know that we are having what, four possible choice we can have, right? And then we have to look for whichever is actually giving you the minimum. So let me write this 4 here, right? So it is like this. This is gamma naught. It is like this. I just allow the student and come back. Yeah, right. So in one case, put this as 1 here, this is 0 here. In the another case, this is 0 here, this is 1 here. The other case, you are going to have, let us say, this is 1 0 here, this is null here. In the another case, we are having this 1 and 0 here. What does it mean? It means that in the first case, the detector does no change in whatever it is actually receiving. It means that you see that what you observe is actually 1, and you know that if you are having 1, right, in this gamma 1, you have to decide whatever is being transmitted from the transmitter as 1, right? So it means that if in the first case, if it is 1, the detector says 1. If the input to the detector is 0, the detector says 0. It is not going to change anything. That is the meaning of it, right? So detector is not playing any role here. I mean, it means that it actually choose whatever that value of y, whatever it received, right? So the value what actually received, this y, it is actually chosen as it is in the case of this first. But in the second case is actually interesting, right? So in that case, it is actually having here is when you give 0, the detector says 1. When the actual value of this y is 1, the detector says it is 0. It is actually inverted in this case. So that is the second case. This is the second case here. And the third case, irrespective of whatever you give as input, right? So either it is going to be what, 1 or 0, whatever you give, you always, right, declare them as what, 0 only. You always declare them as 0. So you see that, right? So you always declare them as 0 irrespective of whatever you get here. So, and the last case is the other way around. Irrespective of whatever you receive in the receiver section, the detector is going to declare, right? So the third one is over now. The detector is going to declare always it is going to be 1 in this. These are all the four possible rules actually I am going to have, right? So you have to see which rule if I impose, right, based on the prior probabilities and all, right? That C bar value is actually giving me the minimum. That rule I have to use it for the detector, and hence this detection is actually achieved, right? So now we will consider this particular case. We have the channel characteristics here, right? So this is P of 0 given 1. Please correct it, right? So this is P of 0 given 1, right? So the other things are understood, right? So because in the channel characteristics, right? So it is like this, this is 0 here, this is 1 here, this is 0, and this is 1, right? So when I am saying this one, no, this is what, this is probability of 1 given 0. You are getting 1, but when 0 is transmitted, this value is going to be what, 0.6. And here I have written probability of 0 given 1, it is 0.2. It means that you are getting 0 when 1 is transmitted, so that value is actually 0.2, right? This is enough to understand what is that value of this, because you know that probability of what, 1 given 0 plus probability of what? 0 given 0. The condition should be the same. You have to be careful in that. The condition should be the same. Condition on the same thing. And this 1 and 0 is actually becoming what? The partition. This 1 and 0 is actually becoming partition. So if I do this, it should end up with what? 1 here. So this probability of 1 when 0 is transmitted, right? So that is 0.6. And hence this value, what you are having here, that should be 0.2. And similarly, here this probability of 0 when 1 is transmitted plus probability of 1 given 1, right? When 1 is transmitted. Given the same condition, 1 here, the 0 and 1 that forms the partition. So this should be end up with 1 here. So we know that probability of 0 given 1, it is 0.2. So this is given as 0.8. So to understand this channel matrix, it is good enough that these two information is given, right? Other things we can actually calculate, right? So now the prior probability, what you see here in this graph, right? I am going to discuss this one in detail, right? So this is what is prior probability. I am using a different notation, right? So P naught here it is given. In the previous slide, I have used the notation pi naught. So don't get confused. It is about this prior probability of 0 being transmitted, right? So both are same, right? So this is a prior probability. And different probabilities, right? It is actually going to have the range from 0 to 1, right? For this arbitrary prior probability, I'm not going to fix this prior probability as some value. I'm going to treat this arbitrary prior probability. Then what is my base cost for all the 4 rules, right? So we have like rule 1, we have rule 2, and then rule 3, and then rule 4. We know that, right? So quickly we will write what is that expression for that rule. So rule 1, you know that gamma 1, okay, gamma naught is 0, and then gamma 1 is going to be 1 here, and then rule 2, it is gamma naught is 1, and then gamma naught, I'm sorry, gamma 1 is going to be 0 in this, and then rule 3, gamma naught, let us say that it is 0 and 1, and gamma 1 it is null here, and then the rule 4, it is gamma naught, it is null, and you have this gamma 1 that is going to be your 0 and 1. So you have, so now I just wanted to know what is my cost function, this C bar for this rule 1. C bar, you know, right, with of course with the assumption that C10 is equal to C01, that is equal to 1, with that, you know, equal weightage for both the error, right? So you know that expression, it is pi naught into P naught of gamma 1, right, plus pi 1 into P1 of gamma naught. This is what the probability, I mean C bar expression. So now I said I'm not going to use this pi naught as a some value, right? I'm going to treat this pi naught as a variable itself, so it is pi naught only. But you see this, what is that rule 1? As far as this rule 1 is considered, this gamma 1 is 1, gamma 1 is 1, and your gamma naught is 0. It means that what is that probability that, you know, you are getting 1 when 0 is transmitted? So that is, you know, so that is what this probability is giving you, right? So what is the probability of 1 when 0 is transmitted, right? This is this probability of 1 when 0 is transmitted, which is actually the 0.6. So it is 0.6 here, plus I use that same color here. So this is into that 0.6 plus, of course, this pi 1 I can write it as 1 minus pi naught, right? So because I wanted everything in terms of this pi naught, right? So this one is gamma naught is 0. So what is the probability that getting 0 and 1 is transmitted, right? So it is probability of getting 0 when 1 is transmitted, that is going to be your 0.2 in this. So you are going to have 0.2 in this expression, right? So it is going to be the straight line. That is what I just wanted to say, that it is 0.6 pi naught minus 0.2 pi naught plus 0.2. It is like that. So you are getting this expression as 0.4 pi naught plus 0.2. It means that when pi naught is 0, the cost value you are getting it as 0.2. When pi naught is 1, you are getting this cost function as 6.6. You see that when this prior probability is 0, your cost function is here is 0.2. And when this pi naught is 1, you have a cost function value which is 1, 2, 3, 4, 5, 6, which is 0.6 here. And you have a straight line. This is the straight line. This straight line is the rule 1. This is the rule 1 you are having now. Because I am not fixing this, prior probability. So for various prior probability, you are getting that straight line like this, right? So let us quickly do it for the other combinations also, right? So this is anyhow, this is going to be like 0 given 1. Okay? So now we'll quickly calculate for rule 2. Rule 2 is C naught is what? Pi naught. There is no doubt in it. I think I'll use this expression. I'll write the final expression here. I'll use it here. We know this expression is the fixed one. But what is going to change now in rule 2 is gamma naught is 0 and gamma 1 is 1. Right? I'm sorry. Yeah, gamma 1 is 0 and gamma naught is 1. It is just reversed here. It is just reversed here. You see that gamma naught is 1 and gamma 1 is 0. So it is just reversed. So what does it mean is that probability of 0 getting 0 when 0 is transmitted here, probability of getting 1 when, right, 1 is transmitted. That is what we need, right? So what is that value here? Probability of getting 0 when 0 is transmitted, which is actually this 0.4. I hope this is clear to you, right? So it is 0.4 pi naught plus, in place of pi 1, I'm going to write it as 1 minus pi naught. And then probability of getting 1 when 1 is transmitted, that probability of getting 1 when 1 is transmitted, which is 0.8 here. So you are going to have this 0.8 in this expression. So you get this 0.4 pi naught plus 0.8 minus 0.8 pi naught. So it is minus 0.4 pi naught plus 0.8. It is having the negative slope, right? Right. So this is the negative slope. Let us say that at pi naught equal to 0, you are getting that value as what? 0.8, right? When pi naught is 0, this is that 0.8 here, right? So this point, when pi naught is 0, you are getting this value as 0.8, but when pi naught is 1, right? So you get minus 0.4 plus 0.8, which is 0.4 here. 1, 2, 3, 4, and this is what you are getting. And this straight line, what I am showing here, straight line is for the rule 2. This is rule 2. This is rule 1, this blue color, what you see here, and this one is that rule 2. So both are actually Bayes cost, right? So both are Bayes cost what you are having. Okay, quickly once again we'll do it for case 3, then you can understand clearly that, right? So we'll go for this case 3. Case 3 is very simple, right? So because your gamma 1 is null set, when this gamma 1 is null set, this probability is actually becoming 0. This probability is becoming 0, and your gamma naught is a universal, I mean the complete 0 and 1. So this probability is actually becoming 1 in that case, right? So in case of rule 3, this is becoming 0, right? And this is becoming 1. So it is C bar is simply 1 minus pi naught, because it is actually giving you that pi 1 is 1 minus pi naught, right? So 1 minus pi naught means when pi naught is 0, you get the value as 1 here. When pi naught is 1, you get the value as 0. So this straight line, what you see, right, this straight line is what we call it as this rule 3. This is rule 3. And similarly for the case 4, that is a rule 4, right? For that case 4, this is actually becoming 1, just the ulta what you are going to get, right? So this one you get it as 1, and this one you get it as 0, and case 4 you are getting that C bar is equal to what? Exactly this phi naught. So this one, this straight line what you see here, this one, right? So this straight line is what we call it as this rule 4, right? So now this figure whatever you are seeing here, we have this all the rules, right, as a function of phi naught. So for the prior probability we are getting that, right? So now among these 4 values, whichever is actually giving you the least, that rule only I have to choose. For example, let us consider this is a prior probability, right? So what are the possible, right, rule and the corresponding base cost you are having? Say this is 1, this is the another, and somewhere here this is going to be that another, and this is going to be that another, right? So we have actually 4 rules, right? So this is the first rule, I mean rule 4, this is rule 1, this is rule 2, and this is rule 3. Among these 4, whichever is minimum, the minimum is this rule 4, right? So now if my probability is this, right? So we don't know that exact number, maybe this 0.4, 0.2, I think 3, 4, 5, 6, 7, 8, 9, 10. Yeah, this is 0.2 here. Suppose my prior probability is 0.2. If my prior probability pi naught is 0.2, I have to go for the rule 4. So it is basically the function of this prior probability. I am actually fixing the rule. That is what exactly what I want to convey, right? So we can actually see, right, if this prior probability pi naught, right? Okay, I'll erase this one now, it is not needed. So if the prior probability pi naught, if that prior probability is 0.2, then we have to actually go for, what is that? This is that rule 4. We have to go for rule 4. Okay, fine. Let us say this the prior probability pi naught is somewhere in this region, right? See, for example, 0.1, 0.2, 0.3, 0.4, or 0.5, right? Let us say this 0.4. If it is 0.4, right, the prior probability is 0.4. Which rule I have to use here, right? So this is at 1, 0.2, 0.3, this is 0.4 here. For this 0.4, I have cost function, this is there, and this one is there, and this one is there, and then we have this one, right? So among these 4, this one is minimum. This is actually the rule 1. So if it is 0.4, then I have to go for rule 1, right? So now we can actually choose something like 5, 6, 7, right? Let us say this 0.7. I choose this 0.7, right? Then I have here this one, and this one, and this one, and this one. Among all the 4, this is going to be the minimum. This is which is actually the rule 3. So if my pi naught is 0.7, you have to go for rule 3. And interestingly, there is no way that rule 2 is coming into picture in this figure. For any prior probability, this rule 2 is not the minimum. That is the interesting point, right? So we can think that after this green marking, whatever this green marking is there, that's going to be that minimum cost over the function of pi naught. For every values of pi naught, what is the minimum cost you are achieving, right? This is the minimum cost what you achieve, and this is the minimum cost here, and this is the minimum cost here. Over the range from 0 to 1, this prior probability pi naught, you are going to have that minimum cost that follows this green color, right? What you see here, it always going to be like this shape, right? So we also, it is going to have 3 partition in this, right? In all other combinations, whatever the channel matrix it is, you are always going to have the shape like this only. right? So you are going to have three parts in it. The first part, it is basically, right, your rule 4, and here this is going to be that rule 3, right? But when it is in between, right, in fact for this particular case it is actually ending up with rule 1. For some other channel matrix, this will actually end up with rule 2 also. For, of course, for this particular example, it is rule 1. In more general, we get this 3 partition region. It is always that this first part ends up with rule 4. This part always ends up with rule 3. That one never changed. And here is the middle one, this rule, that one we have a choice actually between this rule 1 or rule 2, right? It all depends upon the channel matrix. For this task, it is rule 1 only, right? For some other combination, you may end up with what? Rule 2 here. Here only it is going to change. But this part and this part, always it is going to be rule 4, and this is going to be that rule 3. You can see another example here. So the similar approach, if you do, right? So here, this is, let us consider this example here, right? So this is 0 given 1. A similar approach, if you do for this combination, right? So you see that also you can see here, one case I have chosen greater than 0.5, the another case I have chosen less than 0.5. You see that probability of getting 1 given 0, the channel matrix is 0.6, but probability of getting 0 when 1 is transmitted, it is
could continue the classes.
Are you able to hear now? Yes. Are you able to see the screen? No, just a moment. Hello, are you able to see the screen now? Hello, am I audible? Yeah, yes, fine. Right, so we are discussing this only. So then, so this is rule 4, this is rule 2 and rule 3 we discussed, but you have to see that corresponding 0.6 given 1, it is 0.2 in the first case. One, and this case, this is less and this is greater. This is given 1. This is greater. So in this case, it is actually reversed, right? So this is coming as rule 2 in this. And finally, right, both are greater than 0.5. That is the thing what is selected here, right? So in this case, you are getting that as usual, and this one is this, right? And one is rule 1, and this color is going to be your rule 2. It means that, so this one anyhow it is going to be rule 4, there is no doubt in it, and this one is going to be your rule 3, but this particular example, the middle one is going to be your rule 2. So I have actually explored all possible combination to make you understand. So we have this the channel characteristics, probability of one given 0, that is 0.6. The other way around, it is less than 0.5, that is 0.2 here. This is greater than 0.5 and this is less than 0.5. That way it is chosen. The middle one, rule 1 is coming. Rule 1 is coming, and left side greater than, I mean less than 0.5. The right hand side is greater than 0.5. In that case, you are getting rule 2 in the middle. And the finally, both are greater than 0.5. In the case, you are getting this rule 2 which is in the middle. And remember that this region is always rule 4 and rule 3 in all the case. There is no change in it. Right, over some range, right, up to PL, and from PH, right, so the lower threshold for this probability and upper threshold or a higher value, right, for this probability, right. So this range, it varies. Actually, this PL is same in all the case, right. It all depends upon the values change. What I'm trying to say is the prior probability, if it is ranging from 0 to PL, the rule is always 4. There is no doubt in it. And then if the probability, the prior is pH to 1, right? So this is that prior probability pi naught, right? So that rule is always going to be that R2, I'm sorry, R3. This one we cannot have any change in that. In between pH to pH, right? We have two in it, right? A to be that rule 2 or rule 1. It all depends upon the channel characteristics, right? So that way only it is structured, right? So let me wind up today's class by asking that final question, right? Okay, fine, right? So you are knowing this prior probability, so you are able to freeze it. In some cases, right, the prior probability pi naught is not available. The question mark. I don't know, for instance, that prior probability. Then which rule I have to choose? Which rule I have to choose? You think about it. That is going to be the next class. What we call it as minimax deduction rule. Minimax deduction rule. What is that? We'll discuss in the next class. The idea is, if the pi naught is not known, then what could be the better choice for choosing the rule? Always Bayes rule is the best. Whatever we have done, that is the best. Bayes rule is the best. Is the best. But that needs the prior probability pi naught. But if it is not available, if it is not known in real time, then I have to somehow fix the rule. In that case, which rule I have to go? To answer that question, right, we are going to discuss in the next class, right, what about this minimax deduction. We'll stop here, right? So we shall discuss minimax technique in the next class.